Great. I think we are recording and yeah. Okay. So hello all. Welcome to this course, generative modeling using VAs. So a couple of things that I wanted to just clear it off before we, start jumping into the concepts. Was that, as mentioned in the flyer, this is going to be a very slow-paced course, right? So which means that we will do a lot of stuff, but it will be done in a slow pace, and all such that all are able to understand exactly what we are dealing with and how it will come useful going forward, right? And second thing, it is going to be a theory-based course. So we will not look at so something that you can't expect from this course is things like, for example, you know, architecture sort of questions. For example, which architecture is better for uh, some predictions or whatever. We'll deal with this in case we go to programming, right? So there I can give some pointers as to, what sort of things have worked for people in the past. But other than that, I think we'll not be looking at different architectures. For example, we'll not be doing like how does Lenet or AlexNet, those sort of architectures, work in this particular framework and stuff like that. So, whereas what we will be doing is looking at mainly VAs primarily, and their complete theory that underlies them, all the required assumptions and what happens when you violate those assumptions, etc., is something that we'll be dealing with in detail, right? And as mentioned, we'll have the recordings done and class notes will be available. Ideally, this particular notes is also should be available in the files tab. So you can just check that. And this, I guess, so as and when I'm writing, you can just keep on seeing that, the class notes will be available. You'll also get a certificate for completion, and I have decided to do it based on attendance. We'll not have any exam or anything to, to keep it light. And any discussions during or after the lectures are all encouraged. So feel free to ask a lot of questions. And if I'm able to answer, well and good. If not, I can go back to people that who know this stuff more in more detail. I can get those clarified in the coming lectures, right? Uh, okay, so with that, we'll start the first class. So I am a PhD student in IIC. I am offering this course for the first time, and we'll see, how things go about, and exactly what stuff can we cover in how much time, etc. All that I'll get an idea from this particular course, and then hopefully for new courses we might I might be able to design them better. Um, do you guys want to tell anything about yourself, like what you guys, what your background is, what you're expecting from the course and stuff like that? Maybe Diwakar can start.
Hi, my name is Diwakar. I'm currently working as a computer vision developer. Like majorly, my aim of joining this course is like reskilling and upskilling the about the VAs, like variable auto encoders, related things. Uh, that's about.
Okay, okay, thank you. And Ganesh?
Yeah, so I'm currently doing online BSc in data science and I cleared the gate in statistics. So
Okay.
I might join MTech in artificial intelligence. So I'm
Okay.
looking forward to this course to learn new things.
Right. Okay. Got it. Okay. So yeah, so this helps me to understand too, I can tailor the examples also to the kind of people are there. So again, that will be helpful. Good enough. Uh, okay, so with that said, today we'll look at some very basic probability related stuff. Again, because and we'll go into the exact problem statement for generative modeling, etc. in probably the third or the fourth class. For the first 3 4 classes, we'll deal with some prerequisite stuff, which will help us understand the theory behind VAs. So today we'll look at recap of probabilities. So One very simple example and kind of the example that actually motivated the whole of probability field to come up was in gambling, right? So for example, let's say I have a six-sided die, and if that is thrown, we want to know what side is more likely to come up on a particular throw, right? And then we go ahead and define something called a sample space. Sample space is basically all the possible outcomes that can come for a particular question that we're asking, right? So here we know that a six-sided die has six values on each of them, unique values, and there's 1 to 6, and that becomes a sample space for this particular question that we're asking. So now let's say a very simple question. If I were to ask, what is the probability of side with 3 facing upwards? So what would your answer be? Again, straightforward stuff, but what would your answer be here? So anyone can answer. I mean, this is straightforward stuff. So
Like a three faces, so okay, 1/6 maybe.
1/6, right? So the side with the number 3 facing upwards is basically this is going to be 1/6. So when we say 1/6, so what is the inherent assumption that we have made in answering this 1/6? Any thoughts on that?
No, it only one iteration duplicates. It is unbiased one.
Yes, right. So it's an unbiased thing. So basically, the assumption that we are making here is that it's all possible outcomes. All possible outcomes are equally likely, right? So uh, uh, there is no chance that, let's say, the probability of 3 coming up is more than the probability of 1 coming up. And since the probabilities have to add up to 1, so therefore we get this idea that, okay, the probability with side 3 coming up would be just 1/6, right? And hold on to this thought, because this will start affecting some ideas that we discuss going forward. And then we come to the idea or the definition of an event. An event is basically a subset of a sample space. So for example, let's say if I define an event E as an even number showing up, we can look at it as a subset of this sample space that we have, as the subset being 2, 4, and 6, right? And then what would you define your probability of E to be? What's the probability of an even number showing up? How would you answer this question? What would this be, and what is the assumption again that we are dealing with?
It will be 1/2.
1/2, yes. And so we're again saying the same sort of assumption that all possible outcomes are equally likely, plus the fact that uh, on a single throw, for example, the probability that 4 comes up doesn't affect the probability that 2 comes up, right? So in some sense that each of these are in a way independent of each other, so it doesn't affect what the probabilities of each of the of the other outcomes are, and therefore the probability of this event happening is just 1/2, right? Okay, so now we'll look at this idea of conditional probability. Conditional probability tells you that what is the probability of an event when another event has already occurred, right? So for example, let's say uh, and we denote that by a symbol P of A given B, right? So let's say I have an event saying that, okay, A is even number showing up on the same die example, and B is that the number is more than 3, right? So now if you want to answer, what is the probability that A given B? So that means somebody has thrown a die already, and they say as that, okay, you know what, the number was more than 3. So then, but now you want to know what's the probability that it is actually an even number. So we know for a fact that um, among the numbers more than 3, there is 4, 5, and 6, right? The even numbers are 4 and 6, right? So now in this reduced subspace sort of a reduced space sample space sort of a thing, here the probability of A given B now changes to 2/3, right? So previously we had it as 1/2, but now it's increased to 2/3. right? So this sort of a thing is called condition probability. Basically, with something that has happened before, is there? I mean, what is the new probability that this event undergoes, right? And one way to compute this sort of probabilities, or one view of it, is from a very simple probabilistic formula sort of thing, where you say probability of A given B is probability of AB by probability of B. So what would probability of AB be? This is basically saying that both A and B should occur, right? And probability of B is just B occurring, right? So if I were to use this sort of an idea, this would just be that what is the probability that an even number occurs and that the number is more than 3, right? So this would be 2 by 6, right? Divided by probability of B is probability of a number greater than 3 is again 1 by 2, right? So this becomes 2 by 3, right? Um, now, another view here is that because B has already occurred in nature, or it has already happened. So we see this sample space as now a reduced sample space in some sense, right? So previously we had a sample space that spanned, all its values 1 to 6, right? But now our sample space is a reduced sample space, which is the possible outcomes which satisfy this the event upon which we're conditioning, that is the event B. So this becomes the new sample space becomes just 4, 5, 6. And now then we apply our basic thought process of probability and say, okay, this is my sample space. In this, again, we assume that all outcomes are equally likely, and then say, okay, what's the probability that an even number occurs? So then again, same thought process. We have two even numbers among the three possible, and everything is equally likely. So this becomes 2 by 3, right? And then when we bring in multiple events, we have the idea of independent events. Now here, as we saw, what happened was, let's say if I were to tell you, I mean, if this was some sort of a game and you have to estimate or bet on this idea that, okay, do I get an even number or not, right? So what would happen here is that, let's say previously, without any information about what the die has happened, your probability of even number coming up was 1 by 2. But now that you know that the number is more than 3, the probability has now shifted to become 2 by 3, right? So this sort of a change in probability happens when we say when this happens, we say that this A and B are not independent events, or vice versa. If there is no change in the probability or the uncertainty about some event happening, then we say that the two events are independent of each other. So basically, if probability of A given B is equal to the probability of A, then we say that A and B are independent events. So that's because B's occurrence hasn't informed anything about the uncertainty or the probability of A's occurrence. So one simple example again is that, let's say if A is an even number, again same thought process, but B is an event which says it's a multiple of 3, right? So if you think about it, what would the probability of A, we already know it's half. What is the probability of A given B, right? Now B, the set, the event B can be looked at as subset of 3, 6, right? And A subset is 2, 4, and 6, right? Now probability of A given B, we can use in multiple different ways, but we'll use a second approach where we look at the shrunken, sample space. So among these events, among these possible values of this, event B 3 and 6, what is the probability that an even number comes up, right? Now the even number among this set is only 1, right? And again, we assume that all outcomes are equally likely, so we get the probability of A given B being half again, right? Now, let's also look at just the probability of B separately. Probability of B separately is 3, 6. So it's two possible values, again equally likely. So 2 by 6, this becomes 1 by 3, right? Now, what's probability of B given A? Right. So probability of B given A is here among these even numbers that we have 2, 4, and 6. There's only one number which is actually a multiple of 3. So this becomes just 1 by 3. Right. So at the face of it, it may seem that these are not independent events, but the occurrence of one event, that is B or A, hasn't helped us in reducing or increasing the probability of the other event anymore. Right. So this sort of events, they're called independent events here in this case. Right. And as we can see that it's a symmetric relation, and there is P of A given B equals P of A implies that P of B given A will be equal to P of B. Right. And this also follows from Bayes' theorem, but again, these are all we don't need it right now for now. Right. And independence we generally denoted by this symbol A perpendicular to B. This basically means that probability of A given B is probability of A, right? So any doubts here in this stuff that we have discussed till now?
No, it's fine.
Okay, fine. So now we'll move on to this idea of random variables. So I'm sure you heard what random variables are. So anyone want to define what random variables are? So what's a random variable as such?
A random variable is a function from sample space to real line.
Right, correct. So we have our sample space. Let's say we call it, let's say we'll denote by S, the sample space that is a set of all possible outcomes for a particular question that we're interested in asking. A random variable, for example, let's say X, is a mapping from this particular set to a real number line, right? Now it need not be exactly real number line, but some subset of real number line is also fine, right? So when I say, so in this example, let's say in the die example, if I were to characterize, the value that came up on the die, right? So it's a bit difficult to see here, but just bear with me. So for example, here the sample space basically is 1, 2 to 6, right? I define the random variable here, let's say X to be the value of the side that comes up, right? So again, the idea, so what all values can X take? So X basically just takes same values 1, 2, and up till 6, right? So X is in a way acting upon the sample that we have and mapping it to a number which is one of these 6 numbers, right? Now in the coin toss example, for example, let's look at a coin toss example. So um, again, so here we have, let's say, a coin toss can give you heads or a tails, right? And if I want to understand the outcome of a toss, so I can define a random variable X, right? Which takes in the value, let's say H, and spits out a value called 0 for it, or let's make it a bit more cleaner, 1, and X of T is 0. So your X as a random variable takes values 0 and 1, right? Then let's say, for example, we have a sequence of coin tosses and we're looking at, for example, let's say the number of times the heads come up, right? And let's say potentially we can go this up to infinity, infinite coin tosses. So then the random value X, random variable X takes in the values from 0 to infinity, right? So this is just, yeah, right? So this is the idea. So here basically the idea is that X takes in a sequence of coin tosses as an input, right? Because one sequence is what the sample space has. For example, it takes, let's say, T, for example, and spits out a number called 2 because we're looking at number of heads. Let's say X is defined to be the number of heads. right? X now will also map HTH to 2, right? And so on. That's the idea of this coin toss example, random variable. Now let's say height of a person, right? So in the height of a person, for example, let's say, so what would be the sample space here in let's say when I say height of a person is a random variable, what would be the underlying sample space? Any thoughts? So for example, let's say I want to know the heights of all the people in the world right now, right? So your sample space basically is just the population, right? Population of Earth, right? So this is a very large sample space, and the function that is there h, right? It takes a person as an which is an element of this set sample space S, and measures the height. It takes takes a measuring tape from head to toe and gives out a number, let's say 6 feet, right? And so on. So these sort of things, I mean, the idea here is that what is the underlying sample space that we're talking about, and what is the random variable actually trying to capture, right? That is the point that I want to make here, right? So h as a function is now random because the person that you choose can be random and so on. So h can take actually any value, any real value. Again, that's theoretically. Practically, yes, you'll have some constraints and stuff like that. But theoretically, it can take any real value. You can have 6.1, 6.01, and so on, feet and so on, right? So now we'll come to the idea that so as we saw here, we saw like two types of random variables actually. One which took a discrete sort of a values, and one which took something like a continuous sort of a values. And that's exactly the broadly two types of the random variables we have. One is discrete, other is continuous. And there's a special case of continuous called absolutely continuous, which is exactly what we'll be dealing with, but we'll come to that. So the idea of discrete random variables is that you can take either a finite number of possible values or countably infinite. Countably infinite means you have a mapping from natural numbers to whatever the number of values that the discrete variable can take, right? So for example, here in the sequence of coin tosses, we said that we can go up to infinite coin tosses. So this X as such, that's the number of heads that you got in that particular sequence. That is a countably infinite number of possible values, right? Because you can take anything from 0 to infinity. But again, discrete in nature. You cannot take 0.1 or any float value. So that sort of a thing. So those sort of random variables are called discrete random variables. And then each value in that particular, these possible values can occur with some probability, right? For example, let's say the probability of head occurring, right? For example, let's say how the way we defined here, x equal to 1, right? So let's say that the probability of head occurring is p. Okay, for example, let's say it's a biased coin and p is not equal to half. And so then we can say that this basically also implies that p of x equal to 0, which is equal to saying the probability of a tail occurring is 1 minus p, right? So basically, both the possible values that you have for this random variable, that is 1 or 0, take the value 1 or 0 with some definite probability. You know what the probability is, and occur with that probability only, right? And again, example from the die example that we had just now. So probability of 3 occurring, let's say, is probability of d equal to 3, right? That is equal to 1 by 6 as we just discussed. So this sort of a mapping that takes a random variable as an input and spits out a probability associated with that. It's called a probability mass function, right? So we're dealing with two sort of functions here, right? So one is from the sample space, which goes to a random variable space, let's say, which is, for now, let's just call it R, right? So this is a random variable that we have. and the probability function, there's a PMF for discrete random variables, takes this R, the value that you have here, discrete set, and some discrete set, let's say, right? And this, it takes this values in this discrete set and maps them to a interval 0 to 1, right? And because probabilities are between 0 and 1 always, right? This is called the probability mass function for discrete random variables. Now, this is one sort of function that we have in place. The other sort of a thing is that I can always look at events in this random variable space. The previously when we said events, we said that okay, things like what is this what is the we defined event as a saying that okay, even number occurring on a die throw, right? So that sort of a thing. So here we can again define events in the space of random variables also, and then that basically translates to this sort of a idea. For example, let's say if I ask what's the probability that d is less than or equal to 3, right? Now we know what d stands for, right? So we're saying that d is what is the value that the die came up with, right? So the event that d is less than or equal to 3 is same as the event that the die gave 1, 2, and 3. And so the probability of this d less than or equal to 3 is same as probability of 1, 2, 3 occurring, which is exactly half. Right? Again, under the assumptions that we discussed. And the assumptions basically come out like this, right? So we say that d belongs to 1, 2, 3. And because they're again independent, I mean, they don't affect each other, so we can just add up their probabilities and to get us half, right? This sort of a function is called as a cumulative distribution function, right? So more formally, if you want to give a notation, this is something like this. So we talk about fx of x, that is the distribution function of the random variable x at a value small x is the probability that this random variable capital X will take a value less than or equal to small x, right? So for this particular example of the die throw, this fx or fd, for example, if you want to call it, fd is going to have values at 0, 1, 2, 3 until 6, right? And how it will move ahead is we'll say that okay, this is 1 by 6, 2 by 6, and so on up till 1, right? That's the idea. So this is called the cumulative distribution function, and again this will exist for any and all random variables. So do you want to name any famous discrete random discrete distributions? Any names that come to mind?
Binomial,
Binomial,
Poisson,
Poisson,
Bernoulli,
Bernoulli,
geometric,
right? Geometric,
negative binomial,
yeah, negative binomial,
discrete uniform,
negative binomial, yes, discrete uniform, right? Right. Yeah, this makes sense, right? So again, so we'll majorly deal with this one and this one, and these two are very highly related. But again, we will deal with these two in the coming applications part of it at least, and all of these are again, yes, as we discussed, that discrete distributions. So Bernoulli, binomial, discrete uniform, all of these are basically finite values they can take. Poisson geometry can take up to infinite possible values also. I guess negative binomial, it also will have to take finite possible values under its sample space, right? Right. So now, okay, so this is one type of discrete, sorry, one type of random variables. The other type of random variables we have is something called as absolutely continuous random variables. So this, the definition exactly, if you want to understand and all of that, requires some sort of measure theoretic knowledge. Again, I myself don't have it, and this is something that I think we should look forward going forward. But the idea here is, in the most simplest sense, is that, for example, this random variable, this function fx of x, for this example, let's say we were dealing with the die example, for example, right? If I were to plot it as a function, so how would it look like is, let's say the random variable here, let's say capital D, and this is fd of, let's say, D, right? Where D is a value in D. So let's say 0, 1, and up to 6. So the idea is that this will basically look like a staircase sort of a function, right? And so on. And post 6, this is going to be 1, right? So this will be 1, this will be 0, and so on, right? And as, oh, and by the way, if you think about it, fx of x will always be a non-negative because of the fact that the probability themselves will be non-negative, and the fact that when the random variable, I mean, reaches its maximum value, whatever the maximum value is, right? Max of capital X, your fx of x will tend to 1, right? Um, and when it's going to minimum, it will be just 0, right? Right. Um, Below the minimum, right? Okay. And yeah, so now in case we have a random variable, I mean, which has a continuous form. So here, as you can see, we have discrete jumps happening at the exact values here. But if we have a continuous continuous function of fx, and the fact that it is differentiable at all points, then we say that the random variable that we have at hand is a continuous, absolutely continuous random variable, and we can then define its differential, that is fx of x, as the differential of capital F of capital Fx of x as the PDF. It's called a probability density function. So in some sense, this is telling us how is the probability changing across the values of the random variables, right? So one very one niche point here is that for a continuous random variable, again continuous here I'm saying it to be absolutely continuous random variable, is that the probability that the random variable x takes a particular value. Let's say you want to understand what is the probability that x will take a, where x is a continuous random variable. This is equal to 0, right? So exactly why this happens again requires some measure theoretic understanding, but for now take this as a ground truth. And so this x equal to a is basically the event that x takes a particular value, which is a, and we say that the probability that can occur is actually equal to 0, right? Um, so with this in mind, can we now understand what could be the relation between these two probabilities for continuous random variables? Any thoughts on this? No thoughts. So if you think about it, so probability that x is less than or equal to a, so this x is less than or equal to a event that we have in hand can be written as, let's say this is the event. So this can be written as the union of two events, that is x less than a and x equal to a, right? And less than a plus probability x equal to it. Again, we're using the union formula for union for of two events probability. Plus we get a minus probability that both are happening. That is x is less than, sorry, strictly less than a, and x equal to a. That probability is null because no value of random variable will satisfy that particular event, and so therefore this turns out to be 0. And now we have already discussed that probability of x equal to a is 0. So this will just turn out to be probability of x less than a, right? So only for this continuous random variables, these sort of things happen, right? But for discrete random variables, that is not true, right? In fact, for discrete random variables, if you ever wanted to understand, so x less than or equal to a is well defined, right? Because that is exactly what fx of a would mean, right? But what would probability of x less than a mean for discrete random variables? That how we look at it, look at it as, we say it's under the limit that some epsilon tends to 0, probability that x is less than or equal to a minus epsilon, right? That is something like this, and then we look at is it continuous at its value and so on and so forth. But at the end of the day, these two probabilities are not generally equal for your discrete random variables, whereas for continuous random variables, these two are equal. Again, hold on to these sort of major ideas. We'll see how we apply that in going forward, right? So can you name some famous continuous distributions? Any names that come to mind?
Exponential.
Uniform distribution or score.
Uniform, exponential, yes.
Gaussian.
Gaussian,
Continuous.
I'm sorry.
Beta distribution.
Yeah, so things like, yeah, beta distribution,
Gamma.
gamma, right? Yeah, so there's some famous distributions that generally we will look at, and we'll mostly deal with these two again, very ubiquitous almost everywhere in this one. Right, and now again, so just remember this idea that every random variable has a distribution of its own. It may or may not follow one of these famous distributions that we have discussed already, right? And there will be points where we assume something that follows some distribution, and there'll be good reason to do so. And if it doesn't, then some of the methods may fail, that we discuss, right? So this point just keep in mind. So is there a possibility that we have a mixed random variable? Any thoughts on that? Which is like neither continuous nor discrete sort of a thing. Any ideas what this something like this could be like? So again, I mean, for random variables, generally, if you want to make some sort of arguments or whatever, just try to think in terms of the CDF function, the distribution function, right? So if I have a distribution function which looks like this, right? For example, let's say it's growing, for example, let's say linearly here, and there's suddenly a jump from here to here, right? Something like 1 and yeah, this should be 0 and something like that. So let's say this is fx and this is the x random variable, right? So something like this. For example, let's say you're designing an experiment in which, or let's say you're going for a in a gambling sort of scenario, for example, let's say, right? So there It could be like, for example, there's some game where you say that, okay, if you uh, you know uh, bet on, for example, let's say some number showing up. If you get that exact number, then you get some reward. Otherwise, you get a partial reward sort of a thing, right? Partial probability of success. That sort of a thing could be captured with this sort of mixed random variables, right? So, for example, let's say you say that x equal to, for example, uh, x equal to 1 occurs with probability 0.5, for example, let's say, right? And then I say that x is, occurs in a range 0 to, let's say, 0.8 with some linear sort of, with a uniform distribution like this, right? So the PDF in this range is 0 to 0.0 to 0.8 linear, right? And then it gets one with some defined probability of 0.5, right? So such random variables are possible, and just be aware that they don't always fall under any of these single categories. But although we will deal with single types of random variables only, but these sort of random variables can also exist, right? Okay, so now let's recap the properties of of these random variables. So let's say we have, so what does support for a random variable mean? Any thoughts? What does support for a random variable mean? So, okay, so support for a random variable basically means the values at which the random variable can occur with probability non-zero, right? So for example, let's say I have let's say a biased die in some sense, which is, always gives you more than one value, right? So let's say there's a biased die, which is such that it always the face that comes up after throwing it will always be either 2, 3, 4, or 5 or 6. It'll never be 1, right? Clearly it's biased because the probability is now a probability of 1 occurring is not equal to probability of 2. That's fine, but it's so biased that the probability that 1 will occur will be 0 always, right? So the support for this random variable, the random variable, let's say x, or let's say d, right? D, which tells you what face is going to come up. So the support for D, generally we call it as SUPP of D, is basically 2, 3, 4, 5, and 6, right? So values where there is a possibility of occurring, right? Small, high, we don't care. As long as there's a possibility that a value from that particular range or the particular set can occur, that is called as a support. Now, for example, let's say we are talking about continuous random variables, right? Again, absolutely continuous random variables. So let's say the PDF of a random variable, okay, is something like this. Let's say it's a bimodal sort of a distribution, right? X, and this is, for example, the f x of x, right, which is the probability density function. Then if you want to understand the support for this x, support for this x is basically the values in this range and the values in this range, right? So for example, let's say I'll call this range as A and this range as B, so it's just going to be A union B, right? So support of x is A union B. So any computations that we want to perform in the coming properties, they are all based upon this idea of support. So wherever the support is defined, we use only those particular values, right? That's the idea. So then coming to the idea of expectation. So, okay, so what's expectation, by the way? Because this should be sort of very clear. Expectation of a random variable. Okay, let's make it a bit more simple. Let's talk about discrete random variables. So let's say for discrete random variables, how do you define expectation? So let's say if x is a discrete random variable. So what is E of x defined as? Any thoughts?
Summation of x into probability of x.
Probability of x, right? So this probability is basically the PMF function, right? Probability mass function, and this summation is over x. What all x will you take here? That is basically from the support of x, right? So here x is not just purely all possible values. You wouldn't want to do that. Rather, this x belongs to the support of the random variable capital X, right? Similarly, when x is continuous, right? So expectation of x is defined as integral over the support of x. And let me just make it a bit simpler to write this. So let's say I'll call this support of x, I'll define by a symbol. Let's say this is xi or psi. So this support of x, over the support of x, the the integral of x into fx of x, let's say dx, right? But this fx of x is the PDF of the random variable x. Again, we're assuming x is continuous. That's basically absolutely continuous only in our use case for now, right? Okay. What is the variance of a random variable? This is variance of a random variable.
How much is spread the random variable is.
Right, how much it spreads. So the way we define this random variance of random variable, let's say v of x, is defined as the expectation of x minus e of x squared, and some basic math will show that this turns out to be minus expectation of x, right? Okay, so this is how you define the variance of a random variable. So for us, at least, these two things are more than sufficient for now. We'll see if we need to go into more properties of random variables as we go through the course, right? Now, there's actually something very, very interesting that's happening here, or even here, for example. So that is what we will deal with here. So let's say I have a random variable x, right? So let's say x is the height of a person that you measured, right? Height of a person that you measured. Now, let's say I define a random variable, let's say y, to be x squared, right? So what we're doing is, let's say if x turns out to be 6.6 feet or whatever, and then we say y to be 36 feet squared, right? And so on. So for every x, you can generate a y, and so that's the so because x is a random variable, that's random because the way you choose a person is random. Y also turns out to be a random variable, right? So y basically is a function of x. Let's say I call it as g of x, right? So because x is a random variable and g is a deterministic function, this deterministic function, right? Y also turns out to be a random variable, right? So now a question that I have is, let's say if x follows some distribution, let's say fx of x, or let's make it even more simpler. Let's say x is continuous random variable and it follows fx of x, function for its distribution. So what will be the distribution for y? Will it be same fy? Can I write that y follows fy? Okay, this is a bit confusing. Can I write as y is fx? Do they follow the same distribution? Will they follow the same distribution if y is a function of x? Any thoughts?
We have to use transformation to find the f of y.
Right. So we need to use a transformation sort of a function to understand what will be the distribution of y as a function of the distribution of x, right? And one very simple thought process here, if you want to disprove it, is very simple. For example, let's say if x follows a uniform distribution, -1 to 1. If y follows, for example, if y is defined as x squared, obviously very clearly y only takes values between 0 and 1 because that's the squared values. So y and x can never have a I mean, y and x don't generally will not generally have the same distribution function, right? Um, so then, so with that said, how do you define the expectation of a function of a random variable? That becomes a question, right? So here also we did something similar. We said, okay, what is e of x squared, right? So what does the expectation of a random variable mean? And let's assume for now that we are looking at x continuous random variable. So what would you define this as?
Integration of x square into f of x.
Yeah. So for example, if it's g of x, right? So again over the support of x, right? So this particular definition or result or whatever, this is called as LOTUS, which stands for law of the unconscious statistician. So what this tells is that this is not exactly from the definition, but rather this needs to be proven that if you want to take a expectation of a function of a random variable, this is not the definition, but rather this comes out as a theorem that needs to be proved, right? So the way to go about that would be something like this. You say, okay, that y is a function of x, right? And now you want to understand what is the expectation of y. Expectation of y we know is over the support of y. Let's say this is the support of y, and you say y into fy of y dy, and then expand the ideas from this particular function. So how will you go about doing that is, for example, now first thing what we can do is we can look at something like this. We want to understand what is the distribution function of y, that is capital Y. For example, p of y, capital Y less than or equal to y. This is nothing but probability of g of x less than or equal to y, right? Very simply again. Now, under some conditions for g, right? If g is some nice behaving functions, so has some nice thing properties. Again, I'm blanking on those, but should be straightforward. But here the idea is that we say that this is now probability of x less than or equal to g inverse of y, right? So if g is invertible and monotonic, then this sort of a probability will these two will be equal. Otherwise, we need to look at multiple cases here. Now this turns out to be just the uh, the CDF of x at defined at g or g inverse of y, right? And this we know is fy of y. So if I now differentiate with respect to y on both the sides, what ends up happening is I'll get fy of y equals, this becomes fx of g inverse of y, and then I have d by dy of G inverse of y, right? Mhm, right. And then, so now I can write Fy of y dy as, right, d G inverse of y, right? So this expectation can now be written as integral. Okay, just so expectation. So integral over the support of y, pi into fx of G inverse of y, d of G inverse of y, right? And now we say that okay, G was monotonic and stuff like that. So I'll have a unique x for this. So what we'll do is now this turns out to be support of, so y becomes g of x, right? G inverse of y is the corresponding x, whatever we had. So fx of x, and this becomes dx. And wherever y is defined, we have an x. So wherever x is defined, we have a y. So therefore, from this, we get the support of x, right? Because that's the probabilities where I have some non-zero probability of this. So this becomes a definition. I mean, this becomes the result, which tells that if I want to get an expectation of a function of random variable, rather than trying to figure out the probability density of the changed random, I mean the transformed random variable, I can look at the initial, I can look at the same probability density function PDF, but the integral will now change in this format, right? So, but over the support of x. So this is uh, the idea of this Lotus theorem, right? Now we'll deal with this idea a lot in this particular course, because we will need to keep transforming random variables from one to the other to handle things like, for example, let's say the input to output sort of distributions that we will look at. All of that will rely on this very crucial sort of thought process. Okay, so any doubts till now in the past four things that we discussed? Any thoughts or doubts or anything that you have? No?
No, fine. It's fine.
Okay, sure. So now, okay, so now we'll look at the idea of multiple random variables, right? So let's say I have the same, this height of a person sort of idea. So let's say I have the height of a person with me, but I also measure the weight of the person, right? So now, since the person is a random quantity in the world, so I now have two random variables coming from the same person. That is their height and their weight, right? So what I can do is now I can form a vector of these two of these two variables h and w, and this now can be termed as a random vector, or we also call it as a vector valued random variable, right? This is one example for multiple random variables. For example, let's say I have a dice and a coin that I'm throwing. For example, I throw a dice and then I throw a coin also, and I want to understand all the possible combinations and want to do something about that. So the vector that forms up is basically uh, what the particular face showed up. Let's say D, it can be 1 to 6, or coin value that came up, which is basically 0 or 1, right? Heads or tails. Um, so this is simple examples on multiple random variables, but there is something that's fundamentally different among the two examples that we just discussed. So any thoughts on what is different here between these two? It's something much more fundamental that is changing, that is different between these two. Any thoughts? So think about the sample space in this sense, right? So for example, in the first example, the sample space is just people, persons, right? So let's say I call, let's say P, script P or whatever. So these are all the people in the world, for example, right? Now I've defined two functions over it, the height and the weight, right? And I've got values height and weight which are in the real line space, right? And then I'm going to define a probability over this pair, by the way, right? That is the thing here. Whereas here, your sample space is actually a Cartesian product of two sample spaces themselves, right? So let's say dice sample space is, let's say, D, and coin sample space is, let's say, C, right? So the way that this vector, random vector, comes about is something like D cross C, right? So you sample a die throw, you sample a coin throw, a coin toss, and then you get a value of the for this random vector, that is V, and on this is what you define your probability distribution, right? Okay, so these are again some things to keep in mind, and we'll look at these things later on. So now we saw previously what independence of two events were. How do you define independence of two random variables, right? If you want to understand that does knowing one random variable, does it help me or not, or something like that, how do you understand this independence? So for that, there's a again a more rigorous proof, but the idea is that in random variables, again we'll look at two possible cases, discrete and continuous, right? So in discrete sort of systems, if your PMF, okay, before that, actually, let's try to understand this idea of vector valued probability distributions, right? So here the idea is that your probability function that you were seeing before acts on a pair of values. Again, we are using just two here, so a pair of values. So your probability function takes, for example, let's say in the dice throw example, D cross C. This is the sample space, let's say, and now you got, for example, let's say X cross Y as your random variable space. So X is, for example, takes values from 1 to 6, and this takes values 0, 1. Right now on this space is what your probability function acts on, and directs you to 0 to 1 value, right? So now to understand independence of two random variables, let's say if they're discrete, what we hope for is if you can get the probability distribution, Px comma y of x comma y, right? So this is basically the probability mass function of this set of two random variables x and y at their values small x small y. If this is equal to their individual probabilities, that is px of x into py of y, right? If this happens for all possible values of x and y, right, then it's called, then we term that x and y are independent random variables, right? And in continuous space, this very cleanly goes to fx capital X capital Y of this turns out to be, if it turns out to be something like this, right? Again for all x and y, right? Then we say that x and y are independent. Okay, so yeah, so this is all I wanted to revise as a part of basics of probability. So any questions till now? Anything you want to you want to know before we move forward? Prerequisite I want to do today. Okay, so how is are you guys aware of PSD and PD matrices from linear algebra? So what does a PD matrix mean?
Positive definite.
Right. So how do you define a positive definite matrix? Let's say if I say that A is positive definite, if matrix A is positive definite, what does it mean? So first of all, the idea is that again these are basically square matrices only. That is PD and PSD matrices are generally square matrices. So let's say when we say A is a PD matrix, what does it mean? Is let's say if I have A as a matrix of size n cross n, right? And if I take a vector, let's say x, which is an n-dimensional vector, let's say n is x is n cross 1, then for all x, right, for all possible values of x, that is for all vectors x, right, if x transpose ax is strictly greater than 0, right, then we say that A is a PD matrix, right? And here obviously we don't take the condition x not we don't consider x not equal to 0, because obviously if x is equal to 0, 0 transpose A 0 is always going to be 0. For all non-zero values of the vector x, if x transpose Ax is greater than 0, it's called a PD matrix, right? And similarly, PSD matrix, when you wants to guess what PSD matrices would be, let's say I have the same matrix A n cross n.
Positive semi-definite.
Positive semi-definite, and the condition that it needs to follow is
Greater than equal to 0.
to 0, right? So here we allow the value it to be value for it to be equal to 0 also. So why are these sort of special? Again, they have a huge application in kernel-based methods and stuff like that. But here, for us, a more important idea here is to do with eigenvalues, right? So let's say so PD matrices basically. So can you tell me what is the eigenvalues for PD matrices? What you know properties that they will follow? So these are strictly greater than 0, right? So all the eigenvalues for PD matrices are strictly positive, right? And for PSD matrices, right, this can be greater than or equal to 0. Now this has a huge implication on the invertibility of the matrix, right? Because if you know, the determinant of any matrix can be seen as a product of its eigenvalues, right? So if for example, let's say if I have a PD matrix, right? So if A is PD, right, its determinant is greater than 0, right? So therefore A becomes invertible, right? So all PD matrices are invertible, and vice versa is obviously not true. And if it's PSD, it's not invertible, right? Is generally not invertible, right? Again, all PD matrices are PSD matrices, but I'm saying that strictly PSD. It's not PD, but it's strictly PSD. So one of the eigenvalues turn out to be 0, and then therefore your determinant will be 0, and then A will turn out to be a non-invertible matrix, right? Um, all right, so this is all I planned for today. Anything you guys want to know, or else we'll stop for today here, and we'll resume probably next Saturday.
So where do we use PD and PSD matrix?
Yeah, so this will come to use for us in the in the Gaussian distribution formulation. So for example, let's say um, do I do it here or okay? So we'll look at, let's say, something called as the multivariate Gaussian. Right. So if you're aware of what the normal Gaussian distribution for a single variable, the formula, I mean the PDF is basically like this, right? So let's say if X follows a Gaussian distribution of with mu and sigma squared, then the PDF is something like this, right? 2 pi sigma squared root exponential of x minus mu squared, right? This is the PDF of a Gaussian distribution of a single variable. Now, for multivariate distribution, that is, for example, let's say if x is now actually follows a multivariate normal distribution. So this sigma, that is the variance covariance matrix of this particular x, has to be a invertible matrix, right? And what will also ensure is that this will turn out to be a PD matrix also, right? So this will, the way this distribution looks like is something like this. So it's sigma, yeah, right. And then transpose sigma inverse x minus mu, right? So something like this will come out to be. So the sigma has to be invertible, right? And the way we'll formulate it is basically we'll use this in VAs when going from your data space to latent space, and going from latent space back to data space. So at that moment we need to estimate this sigma, the sigma matrix, and the way we'll do it is we'll assume it to be a diagonal matrix first of all, and try to make its diagonal elements to be all positive. So what will end up happening is it becomes a matrix with positive eigenvalues, right? And that basically becomes a PD matrix and therefore invertible. That's the idea. That's where we will use this idea of PD and PSD matrices. Yeah. Any other doubts for now? Okay, so just to this one. So so are you guys aware of this Taylor series expansion? What Taylor series means, and what does it mean to expand a function using Taylor series. So let's say if I have a function f of x, what does Taylor series expansion of f at a point A mean? What is it doing here? Any thoughts? No. So Taylor series expansion of, let's say, a function f at a point, let's say A, x equal to A, for example, at a point A is given as f of x equals to f of A. This you might know, right? F dash of A plus x minus A squared by 2 factorial f double dash of A and so on. Right? And generally we take A to be, I mean, 0 generally, so that becomes the Maclaurin series and stuff. So anyway, so are you aware of this? Like you might have done this in your.
Yeah, it is used for, I guess, MGF, moment generating function.
Right, yeah, So okay, so I mean, yeah, that's one thought process. The other is okay. So what is the what is something inherent assumption we are making in this expansion? Not inherent actually, but I mean something that people tend to ignore.
Function is differentiable.
Sorry.
Function is differentiable.
Right, and how many times should be differentiable?
Like the function may be like convertible at some time.
Convertible. I don't know. I think we use this to prove conversions in some sense sometimes, I guess. So I'm not sure if that's the requirement. But rather the idea is that f is infinitely differentiable, right? So I can differentiate this f infinite number of times at the point A, at the point x equal to A. I mean, I don't want to use x again, but at A, right? So any examples that come to mind when we talk about such functions? Like this is just is a very strong sort of thing to expect, right? But any thoughts? Some examples, if you can remember, of functions which are like this, which you can keep differentiating how many times you want.
E to power x.
E to power x. Okay. Others? Any other examples that come to mind? Like the most basic class of functions, if you think about, they're also infinitely differentiable actually. Which basic class? So polynomial functions, right? Because after a while, their differential just go to 0. So that's in a way we're saying that it's infinitely differentiable. Any trigonometric functions that come to mind? Which are infinitely differentiable. So for example, like sin x and cos x, right? So they are differentiable at all points and infinitely because they keep alternating between each other, sort of minus, plus, and so on, and you keep on getting differentiability. right? So one thought process that I just want to let you know. So for example, let's say there's a function that I don't know, right? Which are not following these nice examples that we have. But there's some function f, and I don't know how much the function is differentiable. No idea, right? So what I try to do is I'll say, okay, and obviously I cannot go up to infinite differentiability, right? So rather what we want to do is we'll say, okay, we'll expand up to some terms, right? For example, let's say I will say uh, take f of x to, take like first two derivatives, right? I'll say only take this much. And let's say we're doing at a equal to 0, just to keep notations clean. Okay, so f of 0, x f dash 0, x squared by 2 f dash of 0. And I'm saying, okay, I will not, I don't want to do anything more than this, right? So basically, so then all of these terms that were there in the infinite, differentiable in this infinite series, all of that becomes some sort of an error term, right? Because basically what you're saying is I will expand f of x as these three parts only, right? And because I'm not taking the infinite series, I will obviously lose out on some parts of the actual function evaluation, right? So it will not exactly match f of x, but there'll be some difference or some error term, right? So this turns out that there is a good way to this error term has some nice properties that it follows, and this is basically from Taylor itself, but Taylor's, I guess, remainder theorem or something like that, right? So we will use this idea in this Jensen's inequality proof that we will do next class mostly, right? This is one thing that I want to leave you with. Just if you have interest of time, just look at this particular Taylor's remainder theorem. That's one thing that I wanted to leave you with today. Second thing is how many of you, sorry, so are you aware of this ideas of convex functions and concave functions and stuff like that? Convex functions, what they are, and some properties of these convex functions.
For
Any?
convex function, if you double differentiate the function and it is greater than 0, then it is convex.
Then it is convex. A more okay, without differentiability, if you wanted to look at what convex functions are, how would you go about doing that?
If it is a global optimization, if you can achieve.
Yeah, correct. So I mean, those are all properties of convex functions. Yes. So if a function is convex, it'll end up having global minima and all of that. So the way, the least, I guess, restrictive way of defining convex function, if you want to think about, is something like this. Let's say I have 2 points. Let's say x and y, right? X and y, and I have a function f. If the function f follows this property, that is less than or equal to theta times f of x plus 1 minus theta times f of y, right? For all theta belonging to 0, 1, and for all x and y belonging to the domain of f, right? So if a function satisfies this property, right, then we say that the function f is said to be a convex function, right? F is convex function. And then we can look at its derivative and say, okay, if its derivative exists, what there are some properties that it'll follow. If its second derivative exists, and that's exactly what you said. Like if the second derivative, if we take, we'll get it to be, for example, let's say, positive, non-zero. I mean, sorry, greater than or equal to zero everywhere, right? And so on. So now the thought process here. If you want to visualize this, it's something like this, right? So let's say I have a function f like this, right? So if I have, let's say, points x and y, right? So what are we saying? We're saying that I take any, so think about it. Let's say if theta is value between 0 to 1, theta x plus 1 minus theta y is basically any point between these two points x and y, right? So we're saying that the function f at any point between these two has to be less than or equal to the linear combination that I take for f of x, because this is f of x and this is the f of y, right? So so we were saying that the function as such is lesser than this sort of a interpolation that I take between the values at f of x and f of y, because theta f of x plus 1 minus theta f of y is the interpolation on this particular axis, right? Which basically means this particular line, right? So this is a way to define convex functions. Now, and I'll leave you with this. Jensen's inequality is an inequality for expectations, basically, such that um, the expectation of g of x, let's say, is less than or equal to g of expectation of x. I might be flipping the same, but I'll
It's
just
greater than.
greater than. Okay, so so this is greater than g of e of x, right? So the ideas. So what will we discuss if g is a convex function? If g is a convex function, and also these respective expectations exist, so all the e's must exist, etc. Right? So so till now, what have we discussed? The ideas of expectation of a random variable, that is a function of a random variable, e of g of x, and then a convex function applied to uh, a function which is just the expectation of x. And to prove this, we'll use this idea of Taylor series and convex functions, obviously, because we're proving for g convex idea. And then we'll see how this gets applied in the VA formulations, right? I guess yes, this is where we'll stop for today. Any other questions or doubts as such? No? Okay, so we can stop here. So do let me know if you have any questions or doubts on Teams also. I'll also stop the recording and stuff. So so